Welcome back again for session 3 of BE Civil Structural, here where we will talk about wind load according to ASCE 716 and the IBC 2018. We will use the same approach that we used in the previous session, here where we will divide it into three parts. The first one we will talk about the code itself. However, because the wind part is very large and has many topics, we will just focus on the most important points. There will be a lot of parts that needs from your side reading. Also, the second part we will have like a brief summary for the main points, and the last part we will explain exam ideas through some examples and questions. So let's start. The wind speed, according to the definition of ASCE 716, it is a wind speed that is measured for 3-second gusset at a height of 33 feet above ground in exposure C. The wind speed is not uniform. Okay, so if I draw the ground, the wind speed it will not be like this. It will not be a uniform. It will, however, it will have a parabolic shape. So the speed is different at each height. So to have like a baseline for this for the wind speed, and we all agree about it, ASCE uses the definition of a height of 33 feet. So when he tells you that you have like a wind speed is equal to like 30 meter per second, okay, then this speed is at a height of 10 meter for exposure C, and it is based on 3-second gusset. Okay, because there are other codes that uses different duration. Maybe he will use like not 3 seconds but will use like 3 minutes. Okay, so it is different. So in ASCE it uses this definition. And as we talked before, the exam may have some theoretical questions. So in you have a question like the basic wind speed, it is measured based on what? He will give you the first choice based on 3-minute gusset at 33 meter, not feet, ground exposure C. So he will give you like 4 choices, and you must choose the correct one, which is based on 3-second gusset at 33 feet or 10 meter for exposure C. The second part we are going to talk about is building classification. It is very important, especially for the building that is susceptible for wind loads, because according to their classification, it will have an impact on the internal pressure. So here I give you a brief of the criteria which determine what classification the building will be. Where it is the classification can be enclosed or partially enclosed or open. This one, which is partially open, it is added in ASCE 716. This classification wasn't existed in ASCE 710. However, in ASCE 716, it has been updated to include this one. So the criteria, as you can see, is that for the enclosed, the area open is lesser than these values, and the internal pressure is the last column. It will give you the internal pressure. It can be positive or negative, so it has dual signs. Each one has a dual signs. So let's give like an example of how you are going to define the classification, because this one it has a high probability to be in exam. So if he like give you a building, so I will draw like a building here. So this one is wall 1, and this one is 2, the one is 3, and the last one is 4, and of course this part is the roof. So he will give you like the area open, or he will give you like the dimensions. It's like 10 meter, the height is like 5 meter, and the bay is 20 meter, and so on. And he will tell you that this part has some area open, and this one has area open, the area open of wall 3. The best approach for this example that you have to make a table, okay, and you will do it like that. Item or wall. So I have a wall 1, wall 2, wall 3, and wall 4, and of course the roof. And you will in this column you will put the area growth. So you will determine the area growth for each one of them. And in the exam he will give you the area open, so I have an area open here. So you will put another column, and you will also write the area open for each one of them. Okay. So the first one, the first criteria that you are going to check, in my opinion, the easiest one, it is the enclosed. ASCE 716, it mentions that the building that has a total area of openings in each wall. I highlighted the in each wall because if a wall, I have 4 walls and a wall of them doesn't satisfy this criteria, then I cannot classify it as an enclosed. Okay, so it mentions in each wall. If the area open, I will check it is a lesser than 0.1 area gross or 0.37 meter square. If none of them, if a wall of them is failed to satisfy this criteria, then it will not be enclosed. No, it will not be enclosed. Okay. The second, and if it is not enclosed, it is better. The second criteria that I am going to use, I will go to the open. I will not go to the partial enclosed, because the partial enclosed, it has a lot of criteria. Okay, I will not go through that. I will check the second one, which open. Also in ASCE, it mentions that a building that has each wall. So I have the criteria must be occur for each wall. So in each wall must have the area open is more than 0.8 area gross. So I will go and put another column and check. Okay, let me and I will put it like here, and I will check the area open is less than or more than more than area 0.8 area gross. So if all the elements, okay, if all especially if all the walls satisfy this criteria, the area open is more than that. If each wall satisfy at least 80% of open, then it will be classified as open. If none of them occurred, then I will have to go to the partially enclosed. Okay, what does it mean by the partially enclosed? Let me start a new one. So still I have the same building, 1, 2, and 3, 4, and of course the roof. Okay, let me start with this one, the wall 1. So I will have the area open in wall 1. It mentions that the criteria that the first one, the area open is more than 1.1 area OI. Okay, the area open envelope. What does it mean by the area open envelope? Okay, what is the area envelope? Open envelope means that the opening of the other walls and the roof. Okay, so I will have it is more than 1.1 of area O2 plus area open for wall 3 plus area open for wall 4 plus area open for roof. So if this criteria satisfied, then that is the first one you need to satisfy. Okay, because it has 2 criteria to satisfy, not 1, unlike the others. The enclosed, it just mentions that the area open is lesser than the smaller of that, and the area and for the open classification, it mentions that the area buildings that each wall at least 80% open. However, for the partial enclosed, the first limit or criteria, the area open is more than 1.1 the area open envelope, and as I told you what does it mean by the envelope. And the second one, the area open is greater than that, this values which is used for the enclosed, and the area open envelope divided by the area gross envelope is lesser than 0.2. So I will go for this one. The second limit that I need to satisfy that the area open is more than the smaller of 0.37 meter square or 0.01 area gross. Okay, if I satisfy that, I need to satisfy another value. What is another value? That's the area open of area O2 plus area O3 plus area O4 plus area roof. Okay, all of that divided by the area gross 2 plus area gross 3 plus area gross 4 plus area roof gross roof. The division of them is lesser than 0.2. Okay, it's lesser than 0.2. So if this ratio is lesser than 0.2 and the area open is satisfying the both of them, and the first limit is also satisfied, then I can classify it as enclosed, as a partially enclosed. So I can here I say that it is partially enclosed. Okay. So a building classification is very important because, as I told you before, it will affect what? It will affect the internal pressure. So it will affect the design, of course. The second definition that you must need to know is the building, if it is low rise or not, it is not low rise. So if we have like the same building, to know if it is a low rise or not low rise, okay, let me do something like that. Okay, so I have this is one L1 and this distance is like L2, and the height, we will measure the height from this location. Okay, that is the height, that is called the mean roof height. This H is called the mean roof height. And the mean roof height, it depends on the theta, of course, and if the theta is less than 10 degree, it will be this one. We will talk about it later, but let me define the definition of building is low rise or not. So the low rise definition, I have two values. The first one, that the mean roof height is less than 60 feet, which is 18 meter. And the second one is the height is less than the least dimension. What does that mean by the least dimension? L1 or L2, least dimension, L1 or L2. If I satisfy both of them, then I can classify them as a low rise. And if it is a low rise, then it will be a rigid building. Okay, according to ASCE, if it is a low rise, it can be considered as a rigid. And the gusset factor, we will see what does it mean by the gusset factor. It will be equal 0.85. Okay. However, the classification, it is very important regarding the low rise building, because when we will talk about chapter 28, it is dedicated for the low rise building. So if the building is not a low rise building, you cannot use this chapter. And we will find out later that this chapter provide a conservative, not conservative, but provide a lower value from the directional procedure. Okay, so it is better to use it because it will give you like a little steel elements. If you are building like a steel structure, it will give you like smaller section rather than using directional procedure, which will give you larger section. Now let's talk about the diaphragm. ASCE 7 mentions that you can consider the diaphragm in chapter 26 as a rigid if the span to depth for a concrete slabs is less than 2. However, in chapter 12, which is dedicated for seismic, it mentions that the rigid diaphragm can be considered for the concrete filled metal deck with span to depth can be considered as a rigid if the span to depth is less than 3. In wind, if the span to depth is less than 2, and in seismic if it is less than 3. Okay, meaning the diaphragm, if it is rigid or if it is flexible, how it is going to distribute the forces on the lateral resisting system. Okay, so if I have a wall, if I have a building here, that is a building, and the plan of a building, and I have a shear wall. Okay, and the floor can be considered as a flexible. If it is going to be a flexible, then the forces that is going to be transmitted to the shear forces, it will be based on the area method. Okay, so this one will have the half, because that is the half, and the other one will take the other half area. However, if it is considered as rigid, here it will be based on area method. Okay, if it is considered for rigid, then it depends on the rigidity of each system. So if this one is like have a rigidity of 1 and the other shear will have a rigidity of 4, then this one will take 4 divided by 5. Okay, then it will take 80% of the force, and this one will take 20% of the force. Okay, so it is important to know that the diaphragm rigidity will affect on how the forces will be transferred to the vertical lateral system. Also, there is a definition called effective wind area. This definition will affect on chapter 3 for CNC cladding component and cladding, where it mentions that the minimum effective wind area will be the span multiplied by the third of the span length. So let's go and talk about the code itself. As I told you before, that I am going as shown here, I will highlight the most important part that you need to focus on. Like as you can see, the basic wind speed is based on 3-second gusset, 33 feet, exposure C. The building enclosed, the area open, a building that has total area of in each wall. Okay, let me highlight this one. So it gives you like in each wall, so you have to satisfy this criteria for each wall. Also, it mentions the building low rise, enclosed or partially enclosed buildings that complies. So it is this one is dedicated for the enclosed or partially enclosed. The mean roof height is less than 60 feet, 18 meter. The mean roof height doesn't exceed the least horizontal dimension. Also, the building open, the building partially enclosed. So as you can see, I highlighted to you the most important part that you need to get familiar with. Here it gives you like a brief. The chapter 27 it uses the directional procedure, chapter 28 uses the envelope procedure, and so on. Building partially open, this one is new. When ASCE gives you like this gray line, it mentions that this one is added. This is an added new part, like this one. So this one is added. The effective wind area, this one is new. As I told you before, the definition of the effective wind area, the area used to determine the external pressure coefficient for CNC. So this the effective wind area, it is specific for CNC component and the cladding, and it mentions that the span length multiplied by an effective wind by effective width that needed to be less than 1/3 the span length. The tips and tricks of the exam that he is going to use, like this one, he will give you like a part of component and the cladding, and the area that is affected by the wind is less than the minimum area. Okay, and of course you will find the wrong answer in the choices, and you will choose the wrong one. So the mean roof height. Okay, about the mean roof height, let me draw it for you. If you have a building, okay, with a sloped roof, so I have a sloped roof. If I have a building with a flat roof, then this is the edge. There will be no argue about it. However, if the slope is less than or equal 10, this area or this part here is called the eave. Okay, and this part here is called the ridge. Okay, so the height here, it is called the height ridge, and this one called height of eave. So the mean of them, it will be here, the middle. This is called H, mean roof height. Okay, so in the exam he will give you like this slope, it will be something like 12 to 5. Okay, so you need to get the theta of that, which will be an equal, let me say, 41%. That is the theta. Okay, so it is more than 10%. Then the mean roof height that is I'm going to take in this case, it will be this one. Okay, so how about if he give you like a theta, like let me say 1 to 12. So 1 divided by 12 multiplied by 100, it will be like something 8.3%. Okay, and in the example he will give you like some questions that you are going to use the h as we are going to see later. So in this case the theta is less than 10, so the h that you are going to use is h eve. Okay, so it is important to know that when you are going to use the h mean or the h eve. So the mean roof height, it can be the h eve or the h eve or the h mean. Here in the definition, it is the average of the roof eve height and the height to the highest point on the roof. The highest point, it is the ridge point. Okay, except that for roof angles less than or equal to 10, the mean roof height is permitted to be taken as the roof eve height. Okay, it's important because we will going to use it like in the definition of the classification. In the building classification, we already use the h. Okay, so it is important to consider in this case, if the theta is less than 10, I will consider the h is the h eve, and I will check it against this criteria and the second one. Okay, it is important to know what is the h mean. Now we will talk about the wind procedures. According to ASCE, there are two types of procedures that we are going to measure the wind on the building. The first one is the directional procedure, which will result in a higher wind value on the structure, and the envelope procedure. Okay, which is applicable for low-rise building. Here there is some the differences between both of them. Directional procedure, it is the external pressure coefficient used are based on past wind tunnel testing of prototypical building models for the corresponding direction of wind. Okay, they used the wind tunnel tests before, and it is based on and the directional procedure, it is based on it. It can be used for any height. Okay, the envelope procedure, it is specific for the low-rise building. They put a building on a rotating dipole, and it will rotate like a 360 degree, and the wind will affect it from each direction, where he can get a response from each part of the building, from the part of the roof. When we will go to chapter 28, we will see about it. Another important thing is the sign convention. Okay, positive means that it acts towards the surface, and the negative means acts away from the surface. So if I have like a wall, so here I have a building. If the pressure at that is the external surface, and that is the inside. Okay, so I have outside, that is outside, and that is inside. So for the outside part, for this one, if it is positive, it means that the wind pressure, it acts towards it. Okay, if it is negative, then it moves away from it. So for the inside part, okay, if it is positive, it means it will go act towards it. If it is negative, which is like suction, then it will move away from it. Okay, let me talk about the roof. The outside part of the roof, if it is positive, it will act towards it. If it is negative, it will act away from it. The inside part here, if it is positive, it will act toward. If it is negative, it will act away. It is important to know this sign because it will because there is as you can see there is interference, or there is a relationship between the outside part of this wall and the inside part. These two cases they cancel each other, and this case also they cancel each other. However, like in the case if it is like here positive and this one is negative, so they will be added. So it is important to know the sign. Positive means acts towards the surface, and the negative means act away from the surface. Negative means suction. Now let's talk about the surface roughness and the exposure categories. According to ASCE, there are three different types of surface roughness. There is B and C and D. And the description for the surface roughness B, it is for urban and suburban areas, wooded areas, or other terrain with numerous closely spaced obstructions that have the size of a single family or dwellings or larger. This picture I have taken from the commentary. Okay, that is from commentary. It gives you like a description of what type of surface roughness B is. In the exam, he will not tell you that what is the surface roughness. He will tell you like you have a building in an urban or a suburban areas. Then you will have to understand that it is the surface roughness B. Also, he gives you like a condition if the building is located in this surface in this area of the surface roughness B, it must satisfy like a distance around it. Okay, so if exposure B, which is the surface roughness, exposure B is the exposure category, need to be satisfied, shall apply where roughness B prevails in the upwind direction for a distance greater than 457 meter, and if h the height is more than 9.1, it gives you like prevails in the upwind direction for a distance greater of 792 or 20 height. What does that mean? If you have so that is a building, that is your project, and you have like the wind direction, it will come from each direction. Okay, there is something called the wind rules. The wind rules, it will identify the most prevailing direction that has wind. So from this direction, the wind it will be here something like that, and at this location it will be something like that, and so on. So after drawing the intensity of the wind at your project site, it will find that the most prevailing direction, it will come like if it is the north and that is the east and that is the west and that is the south, it will be the northeast, the northwest. Okay, that is the most prevailing direction for the wind. And so he need to know, identify the surface roughness. What is the roughness? Okay, so if you are located in a residential area, here that is located in a residential area, then you must satisfy the distance to satisfy the exposure category B. Okay, so if I have a surface roughness B, I need to satisfy some limits to so I can apply the exposure B. Okay, the limits is depending on the height of the building. So if the building height is less than 9.1 meter, the radius, okay, I will tell you the radius need to satisfy is at least shall apply upon direction for a distance greater than 457. Okay, so the radius must be more than 457 meter. So if the surface roughness extend for this distance or more, then I will consider the exposure B. Okay, in case of h is less than 9.1, so it is important to use this h. This h, it means what? The mean roof height. As we talked before, the mean roof height can be the h eve height. Okay, in case if theta is less than or equal 10. Okay, in case of h is more than 9.1, it tells you the radius must be more than the greater of 792 or 20 multiplied by h. Okay, 792 or 20 multiplied by h in case of h, and the h is means by the mean roof height is more than 9.1. For surface roughness C, it is like an open terrain with scattered obstructions that have heights generally less than 30 feet or 9.1 meter, like trees. Okay, and also this picture is taken from the commentary. It is a flat open grassland, okay, with scattered obstructions. Then this area will be considered as exposure C. For the last one, exposure D, is a picture. It says that at the coastal area, it is flat, unobstructed areas, and water surfaces. This category includes smooth mud flats, salt flats, and unbroken ice. In the exam, he will tell you like you have a building in at a coastal area. At a coastal area, then it will be surface roughness D and exposure D. Also for exposure D, he mentions the minimum radius around the building, same as for exposure B. It tells you that the direction for distance is a greater of 1.5 kilometer or 1524 meter, or 20 multiplied by the mean roof height, which one is the greatest. Exposure D shall also apply where the ground surface surface roughness immediately upwind of the site is B or C, and the site is within a distance of 183 or 20 times the building or structure height, whichever is greater from an exposure D. What does that mean of this part? Okay. I will draw the elevation of a building, so that is the elevation. Then I will have like the water, that is the land, and this is water. Okay. If this part is like surface roughness B, however behind this surface roughness B there is surface roughness D. Okay, if the surface roughness D is located at the distance, of less than 185 or 183, the site within a distance or 20 times the building or structure from an exposure D, like this one. So I have the building site is this D3, and that is the surface roughness D. Okay, if the distance, as I told you, is less than 183 or 20 multiplied by the h of the building, that is the h. Okay, if this distance is less than the greatest of them, then it will be considered as D. If not, then the surface roughness B will prevail. Okay, however, you must also check the distance if h is less than 9.1 or if h is more than 9.1. You must also check the criteria. If the criteria doesn't meet, okay, doesn't meet, doesn't meet, then what you will going to use, you must use the most difficult, the most conservative one, which will be D again. So if you have a building here and this distance is less than 182, 183, and or 20 height, and that is the surface roughness B, and that is the surface roughness D. If this distance is less than that, then we will have to use surface roughness D. If it is more than that, then I will check for the surface roughness B. If the h, in case of h is less than 9.1, or the h in the case of h is more than 9.1, I will check the limits for the exposure B. If it is satisfied, then I will use B. If not, I will use D. In the exam, he may ask you about the surface roughness and the exposure classification, so it is important to know the criteria of them. Also their location in the code. Okay, here that is called the exposure. Here it will start with the surface roughness, and after that it will ask about the exposure categories, and here it gives you the criteria. At this point, for a site located in the transition zone between exposure categories, the category resulting in the largest wind forces shall be used, like this one. So if not B not satisfied, then I will use D. Okay, so it explicitly mentions that the resulting in the largest wind forces shall be used. Okay. Now let's go back. Also for this part, as I told you before, he will not tell you what surface roughness. He will just tell you the location of the building. If it is a flat, unobstructed areas, water surface, then we will consider surface roughness D. If it is like an open terrain, then we will use surface roughness C. Urban and suburban surface roughness B, exposure B. Now let's talk about the velocity pressure, the QZ. The equation, it consists of 5 factors. In ASCE 7.5 there was another factor which is the I factor, importance factor. However, in ASCE 7.10 the importance factor removed from the equation, and it included a number of maps depending on the risk category of the building. And also it is important to know that the V, the units of the velocity here, for the imperial unit it is in mile per hour, and for the metric units it is in meter per second. To get the wind speed, usually in the exam he will not tell you the wind speed explicitly. However, it will tell you that you have like a building, you have a residential building located in Nevada, located in California. And so you need to get the wind speed from the maps. So you must get yourself familiar with American with the USA states, okay, and know the location of them like Texas and New Mexico, California, Nevada, because he will not tell you the wind speed directly. He will tell you like you have a commercial building located in California, so a commercial building, so it will be risk category 2, so I will use this one. And California, so I will use the value of 95. It is the wind speed in mile per hour, and 42 it is the wind speed in meter per second. So again, he will not tell you the wind speed. He will give you a state. So you have a building located in Nevada state, located in Arizona state, New Mexico state. So you must on Colorado state. So you must know which risk category he is referring to, and accordingly you get the wind speed from the maps. Also, this map, it is for Alaska, and I don't think he will ask you about it. But you should know that is Alaska. Regarding the other factors, like the KZ factor and the KD factor, the KZ factor, it depends on the height and it depends on the exposure. And as we told you before, that if we draw like the air, that is the ground, okay, and the wind speed, definition, it will be at 33 feet for 3-second gusset, okay, exposure C. So if we go back to the slides again, we will find that at height 33 feet for exposure C, the KZ factor is equal to 1. Okay. Also there is the KD factor. The KD factor, it is like the probability that the maximum worst case of the wind acting on the worst location of the building will not occur. So it is usually less than 1. However, this value is almost equal to 1 for the the octagonal shape. Okay, like if I have a building, so the worst direction of the wind, the worst wind that will act at the worst location of building will happen. So it is a probability. So this probability we usually the probability is in this case he tells you that this probability will less than 1. However, like if we are going to use like a hollow section, a chimney, okay, so the wind direction from here will be the same, so the probability that the worst case act at the worst direction, it will be equal, because this it is symmetrical from all direction. So that's why you will find that this value is equal to 1. However, for the main wind force resisting system, I have a building like this one, so the probability that will act at the worst location, the probability is less than 1, okay, because maybe the prevailing wind direction will be from here, and this direction is not the worst case. So it is not conservative to use the KD factor in this case equal to 1. Okay, it is not unfair, it is not fair. Also, there are two factors, which is the KE factor, it is a new factor, okay, and the KZT factor, and they are usually taken to 1. Let me see them. the KZT factor, that is the one here. The KZT factor, it regards the topographic effect. Okay, we usually it is taken to one. Don't like don't invest a lot of effort in this part. It is usually taken equal to 1. KZT, it is usually equal to 1. The KE factor, I think this one will be like here. Okay, that is the ground elevation factor. The idea of this one is, let me tell you. So if you have like a sea here, and you have that is the land, so that is the land, that is the sea, okay, and you have like a part here and another slope, okay, you have a building here and you have a building there. The KE factor, it depends on the density of the air, because as we go up, the density of the air is becoming lesser and lesser. Okay, so if the structure is located at a high elevation, then the KE factor will be less than 1. If it is located near mean sea level, then it is almost equal, then it will be equal to 1. So the most conservative value that we are going to use in the exam, and it is, as it mentioned here, the conservative approximate KE1 is permitted in all cases, and the KZT, it will be taken as 1, like this one. So the KZT factor will be taken 1, and the KZ and the KE factor is equal to 1. So this one will be take it 1. A ground elevation factor, take it 1. Okay, take it as a 1. Regarding wind direction, usually 0.85. Why I said usually? Because if it is like a round shape, then it will be like 1. If it is a square, then it will be 0.9, and so on. Now for chapter 27, where we will be able to calculate the actual wind forces on the structures, whether they are for the main wind force resisting system, whether they are enclosed or partially enclosed or an open buildings, and it can be used for all heights. However, ASCE specified some criteria that the structural or the building must be of a regular shape and doesn't have any response characteristics. The response characteristics, the wind has a phenomenon on the building like the vortex shading and the instability, galloping or flutter and so on. So they specified some limits to avoid these response characteristics. These limits related to the aspect ratio of the building and to the height of the building and to the frequency of the building. So if I have a building of height h, okay, and I have like B1 and B2, the dimensions of the building, the first limit is the h of the building must be less than 122 meters. Okay, the second limit, that the summation, the h must be less than for the B minimum. So it is related to the aspect ratio of the building. Okay, it cannot be. So that is called the criteria of the B aspect. How to calculate the B minimum? To calculate the B minimum, so if I have like stories, number of stories of the building, so each story will be like this one will be B1 and the height will be H1. The second story will be H2 and B2 and so on. So this will be one like an HX and this one will be BX. So the B minimum, it will be the summation of H multiplying by the corresponding width of the story divided by the summation of H. Okay, because in some cases you may have some building like this one. So this one will be like a B1 for an H1, but this one will be like an HX for BX, and this one will be like an HX plus 1 for BX. It will be the same also for BX, and so on. So this will lead to some response characteristics undesirable, like vortex jetting and so on. So we must make sure that the total H of the building is less than 4 multiplied by the B minimum. Okay. The third criteria is related to the mode shape of the building. So you must have to calculate the model shape of the structure. and to make sure that to ensure that the F lowest, the frequency of the lowest mode you have is more than quarter hertz. Okay, it cannot be less than that. So this is the criteria you must fulfill to be able to consider this method and to have a conservative value. If one of them failed to satisfy, then you can use the wind tunnel test. I think it is in chapter 31. The wind tunnel test, you can use it like the designing of the high-rise building, like here. They usually use the wind tunnel test. The main idea of this chapter is how to calculate the shape factor. I will pass this slide. That is the equation that we are going to use. The main idea in ASCE, how to calculate this factor, the CB factor. Okay, so let me write it for you. So now, if it is enclosed, the equation that we are going to use, this one, the B equal to Q multiplied by G multiplied by CB, subtract from it QI multiplied by GCBI. So this one, from chapter 26, we were able to calculate it. If it is in metric unit, in SI units, it will be 0.613 multiplied by KZ multiplied by KZT multiplied by KE multiplied by KD multiplied by V square. Okay, I don't think I forgot something. Okay, this is the one. And for the G, we will talk about it now, but we usually take it 0.85. And the CB from chapter 27. This chapter is made to calculate this factor. The QI, it will be the same for the Q, but it depends on the height that you are going to use, which will affect the KZ. And the GCB factor, okay, it is important to consider this factor. This factor, it is in between bracket, meaning that the plus or minus 0.55 or plus or minus 0.18, it is a total factor, the G multiplied by the CB factor, and it doesn't depend on the method that you are going to use. So if you are going to use the directional procedure, it will be the same, 0.55, 0.18. If you are going to use the envelope procedure, it will be 0.55 and 0.18. Okay. For calculating the KZ, we know that it depends on the height of the building and the exposure of the surface roughness and the exposure, if it is B or C or D. The KZT, we told you that take it as a 1 because we don't have a topographic irregularity and so on. For the KE, regarding the elevation, it is very conservative. It is conservative to take it as 1, so we will take it as 1. And the KD, depending on the shape of the structure, but when calculating a main wind force resisting system, it will be 0.85. The V square, as we told you, he will not give it to you, so you must know what the location of the states that he will give to you in the exam, and get the speed from it. Okay. Regarding the G, the G factor, we usually take it as a 0.85. Okay, so the Gasset effect here. Let me okay, that is the equation of the velocity pressure that we already talked about it. They are 5 factors. The KZ, you can get it from an equation. There is the equation of how to get the KZ. Okay, that is for the customary units. To consider the equation, or to use the table. It is better to use the table. However, if you want to use the equation, that is the one. These values is based on are based on these equations. Now for the Gasset effect factor for a rigid building or other structure is permitted to be taken as 0.85. ASCE considers that the building is rigid if its time period is less than 1 second, and this one is, I think it is in the definition. Okay, in this one, the building or other structure, it is considered to be as a flexible. Okay, that have fundamental natural frequency less than 1. Then it is a flexible. If it is more than 1, then it will be rigid. Okay, rigid. That is the building. That is for flexibility. I know this is rigid. Yes, this is the one. Building or other structure rigid, a building or other structure whose fundamental frequency is greater than or equal to 1 hertz. So if I have a building, 1 hertz is not 1 second. So if I have a building or other structure, its frequency is more than 1 hertz, which is corresponding, the fundamental period is the inverse of frequency. So 1 second or 1 hertz, so they are the same. But to ensure that flexible, if it is less than 1 hertz, meaning that the time period is more 1 second, then it will be flexible. Okay. So ASCII considers that the structure is flexible if frequency is less than 1 hertz, and rigid if frequency is more than 1 hertz. And he will tell you directly if the building is classified as low rise, then it will be considered as rigid. So it is okay to take the G factor as 0.85, as we will see now. So let's go to the G factor, the Gaussian effect. That is the one. Okay, to determine whether a building or other structure is rigid or flexible, as defined in section, so he will give you like a limitation for the approximate natural frequency. He will give you like a simplified equation. Okay, let me talk about it first. This is a place where the low-rise building as defined in section 26.2 are permitted to be considered as rigid. So if I have a low-rise building, then it will be considered as rigid and the G factor equal 0.85. However, if it is a rigid building or other structure, for a rigid building or other structure as defined in section, the Gaussian effect factor shall be taken as 0.85 or calculated by this formula. This part I didn't highlight it like in a rectangular box because it is very difficult, or it has a lowest probability to brought in the exam. Okay, because the Gaussian it will usually take as 0.85. You will not have time to calculate this equation. This one, it has no tips or tricks. You are just going to calculate the G. Okay, so it is better to take it as 0.85. And he will ask you about the shape of a building, like CNC, like if you have like a chimney, if you like have a tank. So there are different topics he can ask you about. So he will not waste. So don't waste your time on calculating the G. Just read it. That the G, the least value for the rigid is 0.85, and it can be calculated from this equation. Okay, for flexibly or dynamically sensitive buildings, as we talked before, like the sensitivity of the building, like this one, if even if these factors are not satisfied, it is better to use the GF factor. The GF factor, this F, it stands for flexibility. Okay, so you can use this one to calculate the GF factor. However, this equation is very long and it's very cumbersome, so he will not give it to you in the exam and just to calculate it. Okay, so don't waste your time on it. Just know that for the flexible building, meaning that its time period or its frequency is less than 1 hertz. Okay, then it will be considered as a flexible, and so on. You just know it is like general info. So for the G factor, as I told you before, it will be taken as 0.85. And if the building classification is a low-rise building, then it will be considered as rigid, and you will not calculate its time hertz. So if in the exam he give you like a building like this one, okay, with a theta less than or equal 10, and you have like the building bay width is like an B1, and the length it will be L1, and the H, that is called the eave. So the mean roof height will be, we can take it as an eave height. This is the eave height. So, and we must check the two criteria. This H is less than 60 feet, or 18 meter, and it must be less than the least of B1 or L1. So if in the exam he asks about the frequency of the building, okay, he asks you about the frequency of the building. The frequency of the building is less than 1, is less than 2, is between 3 and 4, is more than 1, and that is the 4 choices. If it is a rigid building, then if it is a low-rise building, okay, so it satisfies these both criteria, then it is a low-rise building. And the low-rise building, it is meaning that it is a rigid. And according to ASCE, the definition of rigid, the frequency is more than 1 Hertz. Okay, so if it is more than 1 Hertz, then it is a rigid. Then I will take this one. Okay, more than 1 Hertz, not less than 2. You understand the idea. So you will not have to go to calculate all these factors and okay, he didn't give me enough information how to calculate the I and to calculate the G and how to get this idea. No, just know that it is a low-rise building. It will be considered as a rigid, and according to the definition of the rigidity, it is a more than 1 Hertz. Rigid building meaning that it is greater than 1 Hertz. That is the idea. The second, as we talked before, is the factor of the CB factor. The CB factor, it is the whole idea of how to get it, but it will take time. So before getting into it, we must consider the minimum design wind load. Okay, this one, what does it mean? So if I have like a building, I will draw the elevation of the building. So this area will be the windward if the wind is coming from this direction, and this is the area where we consider as a leeward. And of course, this place will have like a force on it, the wind force, and this one it will have a pressure here, and this one will have suction. Okay. So after calculating the wind forces on these two surfaces, we can get the shear due to wind. It will be the summation of the pressure plus the suction. Okay. However, ASCE specified a minimum wind load to be considered. Minimum wind load to be considered on the building, on the main wind force resisting system. This criteria or these limits, this also from the commentary, this minimum wind load for the building type enclosed or partially enclosed, if the element is wall, then we will consider 0.77 kilonewton or 16 BSF, pound per feet square, multiplied by the wall area. And multiplied by what wall area? The windward area, not the leeward, only the windward. So after calculating the base shear from pressure and the suction, I must check the minimum wind on the windward. Okay, so I will multiply by 0.77 for the area of the windward, and to check this base shear is less than this one. If it is not less than this one, then I must consider the minimum. And it is one of the tricks of the exam. After calculating the enclosure classification and calculating the Q factor and getting the CB factor and the G factor and all of that, you are able to calculate the wind here, the wind force on the windward, and calculating the wind force on the leeward. But don't forget to check the minimum wind load. Check the minimum. Always check the minimum. And how to apply the minimum? You are going to apply it on the windward. So the total area of the windward you multiply by this factor. So you will be able to get the base shear on the main building. Regarding the roof, he tells you like take it half of this value, like this one. If you have a roof, then it will be, if it is from the other direction, then 16 on the wall and 8 BSF on the roof. Okay. Regarding the leeward, it doesn't consider the leeward. He just considers the projection of the building. That is the idea of the main wind, the minimum design wind load. So after calculating the wind forces from this part, as we will explain it now, you must check the minimum wind load. Now, how to calculate the main wind, the wind load on the main wind force resisting system? There are two types of equations depending on the enclosure classification. So after defining the classification of the building, whether it is enclosed or partially enclosed, you must calculate the wind force on it. And if it is an open, it will be the same as this one. However, there is no internal pressure. The internal pressure is zero, and the Cn, meaning that the Cn it stand for the net. Okay, we will go and talk about it right now. Regarding the partially enclosed or enclosed building, this one I think it will satisfy our idea. Okay, so I have now the force here. It will be the wind ward. So this area is the wind ward. If the wind comes from this direction, and that is the area where that is called the lee ward. The factor at the wind ward, we will use the CB as 0.8. So we will use this 0.8, and it means by positive it act towards it. Okay. For the wind ward, okay, for the wind ward for the roof, I told you to go to this table because it is very difficult to summarize them, because it has a lot of cases and limitation or different cases. For the section of the building, it depends on the aspect ratio of the L divided by B. Okay. Another important thing to define what is the L and what is the P. The criteria for defining L, it is not a constant dimension. What does it mean? L, it is parallel to the wind direction. So if the wind comes from here, this will be an L. If the wind comes from this direction, then not B, this B will be considered as L. Okay, so the L is parallel to the wind direction. B is perpendicular to the wind direction. Okay, so if the wind force it comes from this direction, regarding the leeward wall, that is the leeward wall, it will have two cases, because each time L is different. So let me draw it to you. So if I have a warehouse, so this is L of the building, or don't say it as L, but this is like P1, and this one will be P2. So if the wind comes from this direction, the L factor in this case it will be equal P2, and B will equal to the P1. If the wind comes from this direction, then the L will be B1 and the B will equal to B2. And according to this factor, the L divided by B will differ, because as I told you, one of them will be the larger divided by the minimum, and in the other direction it will be vice versa, the minimum divided by the larger. So if the aspect ratio is small, then the CB factor, the maximum value of it will be 0.5, and if it is more than 4, then it will taken as 0.4. Regarding the leeward roof, depending on as we know that this area is called the ridge. This one is called the ridge. Okay, this is the ridge. Okay, he tells you that if it is normal to the ridge, is that normal to the ridge, meaning that it is perpendicular to it, not parallel. Parallel is then the wind will be in the out of plane of this slide. But if it is normal to the ridge and the theta is more than 10 degree, so the difference, it depends on the h divided by L. What does it mean by the h? As we know that the h, it will be this one. How about h is equal to Eve? Okay, but he tells you that the theta is more than or equal to 10. So if the theta is equal to 10, then the h can be considered as h eve. But this is the case where he tells you that the theta is equal or more than, so the theta may be like a 15. So I will consider this this is the h mean. So it depends on the aspect ratio of the HL divided by this, give you then the CB factor for the theta. This one is considered here. Let me open it to you from the code itself, because it is you must understand how to use it. This is chapter 27. As I told you, it is valid for all the heights. However, they must be doesn't have any response characteristics. As we talked, what are the response? The minimum design wind load. It is very important to consider them. Don't forget about them. In here, he gives you like a brief how to calculate the CB factor. In determine external pressure is the CB or the CN. This is the figure that you are going to use. And it is better to understand that this one is for monoslope roof or open building. This one is for walls, flat, gable, hip, monoslope. This is the one we are going to talk about. Okay, that is the equation for enclosed or partially enclosed. And he will tell you the QI. It will be taken also the h of the building. It will be taken as this h. Okay, for the Q, it will be taken the height. It will be the Z. Meaning what? As we know that the equation for the Q, it will be 0.613 multiplied by the KZ. To calculate the KZ for the windward wall, I will use this Z factor. So this one, it will be based on this factor. However, to calculate the leeward or for the wall or for the roof, we will take the KZ corresponding to the H. Okay, they will give you the same factor, because there will be no difference. There will be no large difference between both of them. So in my opinion, when to calculate the QI, the QI of the building, this one, when to calculate the QI, it is better, as I told you, the QI, the QH of the windward. What does it mean by the QH? This is the QH. Okay, for the side, for the windward, side walls, leeward, and roofs. And the Q here, it is the QZ evaluated at the height Z above the ground. So for the windward wall, to calculate the Q, it will be based on this the Z, and to calculate the side wall or leeward or the other members, it will be based on that one. However, their differences will not be much great, because there will be no difference. The difference is very minimal. So for how to calculate these factors, this one will be okay. This is the one. The wall pressure, as I told you, the windward will be 0.8. Use them. For the leeward, he gave you like 3 cases, negative 0.5 or negative 0.3, depending on the aspect ratio. This is the L divided by the B, and as I told you before, the L it will be the one that is parallel to the wind. B is perpendicular to the wind. The side wall, all values, it will be negative 0.7. So this is the one. That is the plan. So in the plan here, it tells you that is the windward, so the factor it will be 0.8. For the leeward wall, depending on the aspect ratio, and as I told you regarding this wind wall, then this dimension will be the L. If the wind from the other direction, then the B will be considered as L, and you will get this result, the CB factor. Regarding to the side wall, it will be negative 0.7. The factors on the walls, they are very easy. Regarding the factors from on the roof itself, it is very difficult one, because he gives you like the wind direction. If it is normal to the ridge for the theta, what does it mean by the normal to the ridge? That is the one that is normal to the ridge. Okay, this is one is the normal to the ridge. This is the ridge. So if it is normal to the ridge, it depending also on the aspect ratio of H divided by this one L. Why this one is L? Because the wind direction is parallel to it. So after dividing H divided by L, you will be able to get, and according also to the theta, you will be able to get the CB factor. So it will there are different cases for the h divided by l, and for each one corresponding there are two values also, negative 0.7 negative 0.18. What does it mean? If you see this one, that is the wind word, he gave you like a reverse, reverse line. What does it mean? Maybe some of them will be pressure and some other will be suction. So there are two cases to be considered. Okay, and you, of course, you will consider the case with the most severe. For the lee word, it is easier because like here, if the theta is like 10, then it will be this one and so on. This part, it is better to read it yourself. The first step is to calculate the h divided by l, and to understand that for each direction the l is different. After that, determining the theta, there will be two cases. You must consider the one that is most severe, and for the lee word you can get the CB factor. Okay, if the wind is normal to the ridge, so if the wind is normal to the ridge like this one, that is one is normal to the ridge, okay, or he give you another case, parallel to the, that is the one is parallel to the ridge or normal to the ridge, however the theta is less than 10. So if this theta like 5, so it is almost flat, so it is almost like a flat. So when the wind will act here, it will be the same when act parallel to the ridge. So this is the case where to use the wind is parallel to the ridge, and for the normal to the ridge, however for the theta is less than 10. So you must calculate the theta, because the theta depending the CB factor depending on it. And of course it is the same, he will tell you the h divided by l, and this one he tells you that from the distance 0 to the h divided by 2, the CB factor will be a value, and from h2 to h it will have another factor, and the factor is decreasing. So this part where that is the h, and this is the place where we can consider this h divided by 2. So this area will have CB factor like negative 0.8 or negative 0.19, I think, and this part will have a different, and this another part will have another different CB factor, because the CB factor will not be the same from the start to the end. So he will give he gave you like from 0 to divide to h by 10 by 2 the C factor, and from h to h it will give you a lower factor, and so on. Okay, this part is very important because a lot of questions it has a lot of probability that questions coming from this part. You must read it through very thoroughly and understand it. So after getting the CB factor, the idea of getting the CB factor, as I told you, it is very tiresome. After calculating the CB factor, there is the concern of the GCBI. Okay. So I have like the elevation of the building, and I was able to calculate the wind force. The wind force will be the CB. I will use 0.8, and for the lee word, it depending on the aspect ratio of L divided by B, it ranges from 0.5, negative 0.3, negative 0.2. What does mean by negative? Negative, it means the direction, so it will move away from the surface. And positive, meaning that it will go to the surface. How about the internal pressure? The internal pressure is depending on the classification, as we call if it is enclosed, then I have plus, positive or negative 0.18, and if it is partially enclosed, then I will consider positive or negative 0.55. So I have a case internal pressure, and another case suction. So in case of the internal pressure, that is the case for pressure. What does it mean by pressure? The forces act towards the system, the element. So this one will be like plus 0.55 or plus 0.18, it depending on the classification. That is the pressure case. If I have suction, in the suction case, then it will be away. So in this case, if I consider the suction case, that is going to happen. So if I want to calculate the wind on this part, I will use it like this. The B, it will be equal to Q G CB, subtract from it the QI, the GCBI. So the CB here, it will be equal 0.8 multiplied by Q multiplied by G, subtract from it the GCBI. In this case, I told you I consider the suction, and the suction meaning minus, okay, it will be a negative, so it will be 0.55 or 0.18 minus subtract, it will be positive QI. So they will be added same as I draw it. Okay, so it is important to get yourself familiar with how to calculate the wind, because it is at least 2 to 3 questions will be in the exam, and one of them will be to how to calculate it on the main wind force resisting system, and the other one will be for CNC, for other structures like chimney, for a structural support on another structure. This one I got it in the exam. A structure is supporting on the roof of other structure. So you must get yourself familiar of how you calculated the wind in this chapter. Regarding the opening structure, we calculate the CN factor because the CN factor, because the wind will come. The wind will act from here and also will act from top. So he will get you the CN, the net. He already calculated the top and the bottom, and he only acted on the top. And for the monoslope, the half distance, he considers this windward, and this one is considered as a leeward. And he tells you the wind direction. If it is gamma equals 0, that is the direction, or gamma equal 180, then this one will be the windward, and that is the one will be considered as a leeward. Okay. Also for the gable roof, it will be, however, in the gable roof, gamma equals 0, it will be the same as gamma equal 180 because it is symmetric. Let's go for the monoslope. Okay. Also, this one is acting on the doomed roof. I provided you the steps. The step 1 is to calculate the F divided by D. Then the step 2 is to get which factors that you are going to use. Then from this one to get that to get the CB factor. That is the main idea. The main idea of this chapter is how to calculate the CB factor on the structure. You must read it just like a light reading. That is one for the arched roof. That is one for the open building, as I told you. However, there are two factors here. If the structure, okay, let me draw to you. So if I have a monoslope structure, however, there are some equipment or storage that obstacle the flow of the air. If it is obstacle, if this part is more than 50% of the area, of the surrounded area, okay, area surrounded, then this area will be considered as obstructed. It will obstruct the flow of the wind. And in this case, if it is obstructed wind flow, then it has a different value. If it is clear wind flow, then it is like this. If he doesn't mention you in the exam, it contains something and the area of it is more than 50%, you go with the clear wind flow. Okay, consider the clear wind flow. If there is no information talking about what type of storage or type of equipment the monoslope is protecting it or surrounding it. Also here for the diagram for the pitched free roof, he also give you like the theta, and they consider the CNW and CNL and so on, windward and the leeward. That is for the trough free roof. This one in the other direction, when the wind direction for the monoslope and the gamma is equal to 90, as we saw that this is the place. This is the one where the gamma is equal to 0, and when the wind in this direction, the gamma is equal to 180. This is the one where the gamma is equal to 90. Okay, and this one is the same for all the types, if it is pitched, if it is trapped, or if it is monoslope, then we will consider it, this one. Okay, so you can calculate also the value from it. How to calculate the CN factor? There will be no windward or leeward. Okay, there is no classification when the gamma is equal to 90. So and as the same, it will show you that for certain height, like when this distance is less than h equal less than an h, you will apply this one, and from h2 divided by 2h, you will apply this one. And of course he gave you like two examples because the wind is like reversible, so you must consider the worst case and design on it and design for it. The wind is very long topic. It's very long. Okay, according to ASCE, there are different design wind load cases, and there are 4 cases. And if we consider the direction in the actual design in our work, then there will be 12 cases, like in ETAB model analysis, to consider the 12 wind load cases or not. So you must get yourself familiar with that. Also, the eccentricity the wind considered is 0.15. Okay, the eccentricity for the wind is 0.15. However, for the seismic, when we are going to talk about the session 4, the accidental torsion, it will be 5%. Okay, so the wind load considered as a 15% eccentricity. However, in a seismic considered as a 5%. You must understand the differences, because as I said before, maybe I will ask you like a theoretical question. The minimum eccentricity for the wind acting on the building 15%, and acting on a building for the seismic analysis 5%. Okay. Now, before starting with chapter 28, I just want to highlight that in chapter 27 there are another approach called the simplified approach, and if you have enough time you can read it. But if I were you, I will focus on part 1 because it is the most important one, and if I have enough time I will read it. Okay, but don't get yourself distracted with all of this data, because it is very tiresome, like these tables. Okay, I don't think he will ask you about the tables, and I don't think any one of us using these tables. Okay, so if I were you, I will just focus on part 1, how to calculate the wind force on monoslope or pitched roof, the walls and the roofs and so on, because that is the one where will get the most questions in the exam. Okay, for chapter 28, it is for the envelope procedures, and it is for the law. Part 1 applies to all low-rise building. So if my building, if he gave me like an example and he didn't mention which one you are going to use, I am going to use the directional procedure or I am going to use the envelope procedure, you must first define the classification of the building, if it is a low-rise or not low-rise. Okay, so if it is a low-rise, I can use the envelope procedure, and if it is no, then I will use the directional procedure. So he will not tell you which method that you are going to use. You must know that according to the classification of the building. Okay. Now chapter 28 is dedicated for the low-rise building, and as we talked before, that the low-rise building must satisfy 2 criteria, that the mean roof height is less than 18 meters or 60 feet, and it is less than the least horizontal dimension. And of course this method, it yields the lowest wind force. So if it is compared against the directional procedures, so if I have a building and I want to design it 2 times, one according to the envelope and one according to the directional procedure, the one that will give me the lowest value, it will be this method, the envelope procedure. But to use this method, I must satisfy the low-rise building criteria. These pictures, what it shows that you have a building, okay, and this model of a building, it is set on a rotating table, and it will be getting subjected to like a wind force, from each direction, because it is a rotating table, so it will rotate in 360 degree. So this one, it is not in a static mode. Okay, so it is rotating, and they will measure the maximum response for each part of the building. This method is applicable for the low rise, as I told you. So they in the lab they brought some low-rise building, some shape of the low-rise building, and they did the experiments. So they will be able to get the factors that we are going to use in this part. These are the factors. Okay. So he brought the factors depending on the load case A and load case B, and for the load case A and load case B, there are two cases that he is going to design on it. If the wind force, okay, so if the wind force is acting from this direction, like, because the wind force, it is as I told you before, it is a rotating, so this one is rotating. So depending on, so he will use like a region if the wind is acting through this region. Okay, so the classification of the elements of the building will be like that. This is the 1E, this is the 1, and this 2, 2E, 3E, 4, 3, and 4E. Okay, he will also it will be the same if it is the window corner. Okay, so this is the region that the wind will act on it, so he uses a region. Okay, for each corner he will use the same one, and for each one the elements will be divided like 1E, 2E, and so on. That is called the load case A. So it acting out like perpendicular to the ridge. If the wind is like parallel to the ridge, like this region, that is the region, this one will be considered as load case B. So if that is the load case B, this one will be considered as, if the wind is acting parallel to the ridge. Okay, if the wind is acting to the parallel to the ridge, that is the region the wind that is coming from. So this is called the load case B. And as we can see here, he provided for the building surface for each part, and it is a lot of detailed division classification for the elements of the building: 1, 2, 3, 4, 1E, 2E, 3E, 4E. And if you consider these values, it is usually lower than the directional procedure. Okay, there is another term which is called the A. This A factor, this dimension factor, this A factor, okay, that is the A factor, then A equal A.H. It is a smaller of 10% of the least horizontal dimension. So if I have like an L here and B, okay, then it will be the smaller of the 10% of L or B, or 0.4 H, or H is a mean of height. However, it shall not be less than these values: 4% of the least, so it shall not be less than 4% of the least horizontal dimension, or 0.9 meter. Exception if the theta is from 0 to 7% and the least dimension is more than 90, then A equal 0.8H. And this one is I got it from the notes. It's a good practice to read the notes. Okay, if for building with theta and the least greater than 90, dimension A shall be a maximum 2.8H. It is very important to read these notations, because sometimes in the exam he will give you like an example that's satisfying one of these criteria. Okay, so I have a theta is less than 7 and the horizontal dimension is like 350 feet, so it is more than this value. So the A shall be calculated or limited to a maximum of 0.8H. Limited to a maximum of 0.8H. That is important because that is the tricks in the exam. He wants to understand that you understand each part of this code. So I will not apply the code blindly, but I understand that the A has different values when these conditions have been met. So it's better to read it thoroughly. As I told you, also that is here it differs from the directional procedure. Okay, the directional procedure, we had this one, it will be like Q multiplied by G multiplied by C, and this G factor we consider as 0.85 in the case of rigid building. However, this factor as we already see in case A, root case A or root case B, it is all act as a 1. And the GCBI, it is the same for chapter 26, if positive or negative 0.55 or positive or negative 0.18. So if we go back to the code here, this is the root case factors for the GCB. Okay, it tells you that the external pressure coefficient for GCBF. So to calculate the GCBF, that is the factors. So I don't have to calculate the G factor. So it's another important thing. If I don't want to use the G factor, because why he considered this as a directional approach? Because in chapter 26 he told you if it is a low-rise building, then the G will be 0.85. So it is a constant. So already he gets the factor, the shape factor, and multiply by the 0.85 directly. So you don't go to the hassle of calculating it yourself. Okay. For the parapet, it is important also. I mentioned this one in here. For the parapet, it is important, and the roof hangs. Regarding the roof hangs, I didn't mention that. However, if you have like a roof hang here, okay, this is the windward, and that is the leeward. This part will have the same as this one. So this is one 0.8. This one will be the 0.8. Okay. However, the outer side will be considered as a roof. So it will be considered as a roof. So you will have to go to the roof values for this one. This is the one. So to calculate for the overhang, the wind force will act from two directions. From here it will be 0.8, and this one it will be the same as the one that you are going to calculate on the roof. Regarding the parapet, it is an easy one. The combined net pressure, it will be plus, okay, so it is a combined plus 1.5 or negative for leeward. So if I have like a parapet here, so I have a building, and this is the parapet of it. That is the windward, and that will be the leeward. This one will be plus 1.5, and this one will be suction, okay, and the suction it will be 1. Okay, then it will be a 1. So that is the force, and that is the one will act towards it, and this one will act away from it. So the same goes for the envelope procedure. For the parapet also, 1 plus and the negative, and for the roof overhang it will be 0.7. The GCB factor here it will be 0.7. The GCB. It's better for yourself to read it. Okay. So for the chapter 28, just focus on load case A and load case B. Don't get yourself distracted with the other parts like the simplified approach or include simple diaphragm. Just for the part 2, just read it. And as I told you, I highlighted to you the most important one. Of course, don't forget about the minimum design wind load. It is very important to consider them, and I think I mentioned it here. The minimum design wind load. The minimum design wind load after calculating the base shear for a direction, you must check it against the wall and the roof, of course, and the roof. Okay, so you can go back to the slide with the method of how applying it. That is the one, and you must check it against the actual value that you calculated from the equation. So for the other parts, I don't think I forgot about any of that. These parts, as I told you, you can just read it, these tables and so on. If you have enough time, just have a light reading about it, but don't study it. Okay, so let's start with chapter 29. Chapter 29, it is